In this series of videos I'm designing and building a Z80 based computer system. Now it is possible to put together a very basic Z80 based system in just a few hours, but that's not what I'm aiming to do here. I'm intending to build into it a DRAM and a discrete video display system. That's what we had a look at in the first video, and while we're waiting for the boards to turn up, I have designed some prototype boards that I can build that video system onto for test purposes. I ultimately hope to build a single board version of this machine, but that's for the future. And this entire process will be documented, and I'll be releasing a book that gives lots of information about the individual circuits, all the schematics, everything else that you would need to build one of these. But this is just the second video in the series, and in this video I want to look at putting together a very simple core Z80 system. Now this is kind of the thing you might see on a very simple single board Z80 computer. So this is not going to be the final version of the core system for this. This is just for testing and so that I can get all the timing sorted out for all the peripheral circuits. But I thought I'd show this because it is quite interesting if you haven't done this before, and you might find some of this information useful if you want to do the same sort of thing. So I started in a bit of an unusual place with the previous video, in that I was looking at the video output system. But as I explained in that video, I did that for very good reason. It gave me a lot of the parameters I need for the core system, including the clock speed. So if we look at the spec sheet for the Z80, this is from the Zilog Z80 CPU user manual. It's a very detailed manual that they released when they first released the Z80. It's quite useful, and even if you don't intend to use Z80s, it's still quite interesting to have a look through it and see what this was all about. But you can see that the Z80 is a deceptively simple processor, and that kind of belies the power that it has. It has some features built into it that are fairly unique, and I think are one of the reasons the Z80 has persisted for so long. So in this video we'll look at how to just put together a very basic Z80 system. As I say, it's not going to be the final design. This is just so that I have something I can connect our circuits to for testing. But we have to start somewhere, and so the first thing we need to do if we want to assemble a Z80 system is hook up some ROM and hopefully some RAM to the address and data lines, and then figure out how to drive those through the control lines. So that's what I've currently got on the breadboards in front of us. We've got the Z80 in the center. You can see I've got it hooked up to the logic analyzer, and we'll have a look at this running on the analyzer in a few minutes. So we've got the Z80 itself, and the first thing we need is a clock. So I've sketched out the circuits I've got on the breadboards here. Excuse the crudity of these drawings, but we've got a simple clock generator, and we now know what frequency this has to run at based on our video output. And this is running at around 10.8 megahertz, and that's this circuit down here. And I've also included a reset control circuit. It's worth doing this, otherwise the Z80 can come up in a bit of an odd fashion. So when you first power the Z80 up and start applying clock pulses, you need to hold it in reset until you've sent it at least maybe sort of 10 or 12 clock pulses. If you don't do that, it can go into a bit of an odd state and it won't do what it's supposed to. The other thing we need is some kind of divider. Now, strictly speaking, you don't need this. You could run the Z80 directly from a clock, but because we are going to have some fairly complex peripheral circuits, I need a selection of clock frequencies. Now, we have a very similar circuit to this in the first stage of the video output, and I mentioned in the previous video that that's what we can use for this function, but because it's on the other breadboard assembly, I've duplicated it here. So that's this IC down here but that will disappear and we'll combine those two functions into just a single device in the final design. But from the 10.8 megahertz going in, we divide that by 4, and so I'm running the Z80 CPU to about 2.5 megahertz, and that's quite a useful frequency for this type of design. You might want to run it faster, but one thing to bear in mind is that when you design a system like this, it's fairly important to get your clock frequencies sorted out fairly early on. You can't just start ramping up clock frequencies because it will throw everything else out, and you'll end up with some very weird and erratic behavior. So it's best to get your clock frequencies sorted out first, and that's why I started with the video display. So once we've got the clock sorted out, we need to hook up a ROM, and I've done that. You can't see it, it's behind, it's on the breadboard behind here, and it's just a simple 2732 ROM. It has got some test code in it that we'll have a look at in a few minutes, just a few lines, so we can actually get this to do something. And then, because I intend to build a fairly complex computer system, certain things are easier to build in from the start rather than trying to put them in later and then have to repeat a lot of the testing. Some of these, if you're not used to designing this type of machine, might not make sense at the moment, but I will come back to them in future videos and explain them in some detail. But one of the first things we have to do is look at deciphering the various control output lines that the Z80 gives. And 3 of those in particular are the ones we're interested in this video. They are the memory request, the read and the write lines. They're all active low, and as I say, if you look through the manual for the Z80, you'll see various timing diagrams, and that's normally where I start. I'll start by sketching out the timing diagrams I intend to use for my system. And for example, the Z80 will use 4 clock cycles for the first part of the instruction cycle. That's normally referred to as the M1 cycle. And you'll find through your system that you might need to make use of the various edges, the falling edges and rising edges of the clock, the main clock pulse, to carry out certain tasks to make sure they're done at the right time throughout the entire instruction process. And so you can see this particular set of timing diagrams is for a read cycle. So there are actually two read cycles whenever you run an instruction that ends up with an actual memory read. The first one is the instruction fetch read cycle, and normally you will fetch the instructions from ROM, but it could be from RAM, so it's not a case of it's always a ROM, it's just fetching the instruction. But it's this part of the cycle that we're interested in for dealing with the RAM that we intend to fit into the system. Now, one thing I should point out here, I've got a RAM chip back here, but it's an SRAM, it's just a small 2K SRAM. And this is just for test purposes. This is not to be confused with the 2K SRAM that's in the video display. I'm using an SRAM at this point because it will make the overall explanation of the design much easier, but we will be using DRAM in the final design. So in future videos we'll replace this SRAM with a DRAM or DRAM system. That will be multiple chips, but it's easier if you're not familiar with these to separate the requirements of driving the DRAM with the requirements of the basic system, because it can get a bit confusing if you start discussing them all together. So as I say, I've got a small SRAM here. It will make the initial testing much more straightforward, and we can't use a DRAM until we get some relatively complex circuits in place, and I'll explain why that is in future videos. So there are any number of ways you could go about designing a system using a Z80, but I normally start by kind of deciphering some of the control lines, and in this case, because we want to run some basic test programs, ideally I want to be able to read from the ROM and read and write the SRAM. So we'll start by deciphering the memory request line and the read and the write lines, and they are three lines that are used to control the timing and access to various types of memory. At the same time, I've also included, where it's appropriate, other features I'll be using in the future where they kind of coincide or overlap with a particular part of the design. So in this case, the in-out request system is kind of like the memory access. The only difference is, rather than accessing memory, reading or writing, we are talking about in-out ports, but other than that it's a very similar sort of mechanism. So I started off by putting together this very simple circuit, and all it does really is take these three control lines and it turns them into two control lines. One will go low whenever we're trying to read memory, that's whether it's a ROM or RAM, and the other one will go low when we're trying to write to memory. Of course that would just be the RAM, but it could be in any bank of RAM, or it could be the video RAM. But the point here is these two lines then are the kind of top level arbiters of access to memory. Once we've done that, we need to decide how we're going to reference the memory itself, and again this is not going to be the final design. The top part might end up being fairly close to the final design, but what we're doing here is mapping the RAM and the ROM in such a way that we can reference it from the CPU and be able to tell them apart. So we have the two control lines we just discussed coming in at the top here, and one of them, the write line, goes directly to the write line on the RAM. Whether it actually causes a write will depend on whether we enable the device, and that's what the second control line is for. And the thing here that's going to be most confusing if you're not familiar with systems that use dynamic memory is I'll be constantly referring to things such as refresh, which is this line here labeled RFSH, and this line goes low in the second half of the M1 cycle, and it's an output pin from the Z80, and the type of memory we'll be using, which is the DRAM for the main memory in the system, has some fairly particular requirements to make it work properly, and that's what this line is partly there to control. But because it's fairly fundamental to the way we will be accessing memory, I've included it here, but for now we can just ignore this. Just look at this in terms of when the CPU tries to access memory, it's going to access the RAM or the ROM, and to tell them apart I've put in some very simple memory mapping here, and I've mapped the RAM to 4000H, so it starts at 4000H. It's only 2K, so it goes from 4000 upwards, and the ROM starts at 0, and that's just because that's the reset vector for the Z80. Now, if you don't want to use 0 as the reset vector, you can actually put in place something such as a latch that will temporarily map the ROM into higher address space, but most designs will put the ROM in a bank and then switch banks when they want to access the main part of the RAM, which is what I'm going to do here. I'm also doing that because I want this system ultimately to be compatible with CP/M. So CP/M has some fairly basic requirements, but they are immutable, so we need to make sure that if we want to run CP/M, then we design the system in such a way that it will support that. So very simple circuit, and as I say, I'll come back to the dynamic memory aspect of this in a future video, but for now just bear in mind that this is how this particular circuit is connected up. Another thing I've got in this particular design that I will show on the logic analyzer, and again this will be a bit confusing until we get into the dynamic memory system, but I've built it into the system at the moment just because, as I say, it's fundamental to the operation of the system, so I wanted to start testing it as early as possible. So one of the things you have to do with dynamic memory is refresh it on a regular basis. And as I say, I'll discuss this in a lot more detail in later videos. And the book goes into a lot of detail in this. But in general, you need to maintain some sort of counter in order to know which part of the DRAM you're refreshing at any particular cycle. Most systems that don't use a Z80, you will have to create and design a separate counter circuit. They're normally fairly simple, but it's extra circuitry that you need to build and take into account when you're designing the system. The Z80 is fairly unique in that it has an internal refresh counter register, and it outputs that onto the lower 7 bits of the address bus whenever the refresh line goes low. That's the refresh line that we looked at earlier. One of the issues that we have is that it only outputs 7 bits of data. It's a 7-bit counter, and the Z80 was built way back when 16K of RAM was deemed to be the upper limit that was required, and because DRAMs tended to have a square structure for their arrays, it was decided that a 7x7 address space for the DRAM, internal address space for the DRAM, would be sufficient. So they only included a 7-bit refresh counter register. But we are using a 64K, or will be using a 64K DRAM system. So we need 8 bits of refresh data. So in other words, we need to turn the 7 bits of refresh data into 8 bits. Now, we could of course just simply build an external 8-bit counter. But because this system is partly intended to showcase some of the features of the Z80, I wanted to use the internal counter. And that's where this circuit comes in. So this circuit really takes the 7 bits that are coming out during the refresh cycle, adds an 8th bit, and then it feeds that through to a pair of multiplexers. And the multiplexers are required because there are only 8 address lines on the DRAM chips, and yet we need to use a 16-bit address. But I'll come back to how these work in a later video. Just for now, bear in mind that these circuits are here, and part of the testing that we're doing is to see if this output is correct. But don't worry if it doesn't make sense at the moment. I will come back and explain this later once we get into the DRAM system. So that's what we have so far on the breadboard. We've got the Z80, we've got the refresh control circuitry on the right here, we've got the memory mapping and access control on the left, and we've got the memory in the breadboard at the back. It's just one ROM and one small SRAM. So the next thing we need in order to make this do anything is a bit of test code. So it's in a very simple test program. So this is what's currently in the ROM. Doesn't do very much. When we reset the Z80, it will reset to this vector, and all we're really doing here is loading A with a value of 45 hex, loading B with a value of 5, we're loading HL with 4000 hex, and then in a small loop we are writing the value that's in A, which is 45 hex, into the address pointed to by HL. In other words, we're writing a value of 45 hex to the address 4000. And that's why I mapped the RAM to start at 4000 hex, because that's where the test program expects it to be. There are then 3 NOPs, and the only reason these are here is because it makes it easier to see this area on the logic analyzer. So when we're looking at the data on the logic analyzer, the 3 NOPs, because they're values of 0 on the data line, it's very easy to see these, and it's kind of helps us find our way around the data as the program executes. We then do the reverse, and we read from the RAM that we've written to. So we read the value from the address pointed to by HL, which is still 4000, into the A register, and then we increment HL. We repeat that 5 times, we end up here, we jump back to 0, and we repeat the entire program. Just keeps going round and round. And if we translate those into hex instruction values, this is what we end up with. So that's what's in the actual ROM. So when we start up the system, it should start running that code, and we should see the instruction values being fetched from the ROM, and we should be able to see the values being written to and read from the RAM. I should point out that the address lines for the RAM are all connected to ground, so we're not actually sending an address to the RAM at the moment, and that's intentional because normally that address would come from the multiplexers, but because they're not being controlled as such at the moment, I've just got the SRAM hooked up to the data lines and the control lines, but it should still allow us to write to and read from the particular address that's been selected. I can move the jumpers around to select different addresses just to make sure that it is behaving the way that we expect, but just bear in mind this is just for initial testing so that we have a test bed and we can see if the various timings that we put together are going to work. So I'll get the logic analyzer started up, I'll move the camera so we can see the screen, and then we'll start trying to run this and see what happens. So looking at the screen of the logic analyzer, I've got most of the lines for the Z80 visible on the screen, and at the bottom where we've got this labelled MA bus, that is the memory bus, that's the output from the multiplexers that I showed, and I've got an address for the trigger set as 0, so as soon as we encounter an address of 0, we should start capturing data. So this is what we're expecting to see. So the first instruction is a value of 3E. So I'll start up the processor. I'll actually trigger after it's started so we don't get a lot of the startup mess, which could be fairly confusing to work our way through. So I'm going to power up the board now. It's now running, strung about 200 milliamps, and what I can do now is arm the analyzer and it should fairly quickly trigger. So it has now triggered, and we can see already we've got an address value of 0, which is where it triggered, and the first data value that it's fetching is 3E, which is exactly what we would expect it to be. And as I've said before, you can tell where you are in the read cycle for this. We've got read line, which is the blue line, and when that goes low, which is on the first falling edge after the M1 cycle starts. So this is the M1 cycle, this purple line, and when we get the falling edge of the M1, it's the start of the instruction fetch cycle, and then the first falling edge after that is where the read for the instruction fetch starts. This is not our read of the SRAM. This is where the instructions being extracted or read from the ROM. So we can see we've got 3E, which is exactly what it should be, and then the next value should be 45. So if we scroll through to the next instruction, which is 01, you can see we are indeed getting 45. And what we're interested in here is going through to the part of the program where we are trying to access the RAM, which is at 4000 hex. So that is this instruction, and so if we go through there, that's at address 7, and so we'll go through until we find address 7, and we should see a data value for the instruction of 77, and then we should see an address of 4000 being accessed during a write, and we should then see a value of 45 being written to that address. So we'll keep scrolling through. It's address 3, 4, 7, and here we are at 4000. So at 4000 we are effectively getting to the point now where it's starting to write the data to the SRAM. And if we look along the control lines, you'll see here that indeed the right line is dropping, and that is an active low line, so this is the point at which data is being written into the SRAM. If we keep going along, we should get to the point where it's going to try and read the data back, and that's at address B. So that's at this point. So at address B it loads the instruction. If we go back, you'll see that the instruction here is 7E, and you can indeed see instruction 7E, and if we now scroll across, you'll see that when it accesses address 4000, it is indeed successfully reading back a value of 45. To prove that this is actually working, we'll do it again. I'll reset the analyzer, we'll capture the data again, I'll scroll across until we get to the same address. And sure enough, when we get to the address, we're seeing a data value of 45 again. Now, if I disable the RAM chips, I'm going to just disable it by moving the enable jumper to V+, and that will disable the SRAM. We'll trigger again, and now if we scroll back across to the same address, the lines should be effectively floating when we try to read the SRAM. So address A, B, you can see instruction 7E, and this time at 4000 it's just a floating bus that's being read back, there's no data. If I re-enable the SRAM by putting the jumper back where it's supposed to be, we'll re-trigger, go back, look at the same point in the program again. 8, 9, A, B, instruction 7E, and this time again when we get to 4000 we are reading back the correct value. So in other words, the systems we've got it hooked up, the memory decoding and the various controls that we put in place to decipher what the control lines from the Z80 are doing are currently working. One other thing we'll just very briefly touch on here as we've got this set up. If we look along the bottom here, you'll see that the memory address bus, this is the output from the multiplexers. You'll see that this is going up incrementally in value. So if we just change the scale a bit, you can see that this is counting up. It's kind of jumping because we're doing more than one thing with the address bus. Of course, we're running a program, but at the point where the refresh goes low, which is the refresh cycle, so this is the yellow line. When the yellow line goes low, if we look down at the value on the MA bus, you'll see at the moment at this point it's 5C. Look at the next time the refresh line drops, it's 5D. If we go across, it then goes to 5E and 5F. So each time the refresh line drops, you'll notice that the value is incrementing, and that's because that's the point at which the Z80 outputs the internal refresh register value onto the address bus, and that's currently what's being fed through the multiplexers and what we're picking up on the logic analyzer. And we'll come back to this later, but it's just worth pointing out here that it's coming from the address bus. However, if you look at the value at the top, so if we take this cycle for example, it's saying 61, this is 62, it looks fine, looks like it's doing exactly what we want because that's the actual address coming through. But at this point, notice it's inverted, and that's because the circuit I showed inverts bit 7 of the address bus. Now it doesn't matter as long as we do it every time we access memory, but just bear that in mind for the future. If you're wondering why some of the addresses we're seeing look a bit odd, it's because bit 7 of the address bus is inverted. If you were using the same addresses in the RAM in other parts of the system, you would need to invert that before you feed it to the memory. but because we're always accessing it from the same multiplexers, we can just leave it inverted. It doesn't matter which particular cell we deem to be a particular address within the system, as long as we do the same every time. Okay, so we'll move the camera back. So that's where I am with the design so far. We've got most of the video output circuit sorted out. I'm just waiting for the prototype development boards to turn up. Then I'll build one up and we'll put it through its paces. I've got the very basic part of the CPU system sorted out. We've got the clock, the reset, and we've got the basic control in place for the DRAM and the DRAM refresh. That's not to say that we can hook DRAM up yet. We still need some other circuits to be hooked up to control the row and column address strobes, and also to make sure that we get the correct timing and control for the refresh cycles. But once that's done, we can hook up the DRAM, and we should then be able to replace the SRAM with the DRAM system. And we can then move on and start sorting out the final memory mapping that we'll be using and the bank switching. But the way I'm designing this is we're starting from the ground up. We'll get the basic controls in place, which is what we have here. That's to make sure that we can control reading and writing of the memory system. And all we need to do for the mapping is just expand on the mapping that we've already put in place. So that'll be fairly simple to do that. But as I say, the complex part is in the DRAM control, and we'll look at that in the next video.